In this video, we're going to take a look at a neat application of the dot product. So we need to remember that for the dot product, we use it, you can think of it as vector multiplication. And I'm going to put that in quotes because it's not exactly multiplication, but we can think of it that way. So if we had a vector, let's do just a vector u, and we'll say that the components, are a comma b, and then let's look at a vector v that has components c comma d. If we wanted to do the dot product between those, u dot v, what that would look like is we're going to take the two x components and multiply them together, and we're going to add that to the product of the two y components. And that's it. That's our dot product. And it's important to note that for the dot product, you're starting with a vector or two vectors, and you're ending with a scalar. So that's an important thing to remember when you're dealing with dot products. Don't expect to get a vector out. It's the process of turning a vector into a scalar. So that's the definition of a dot product. And now what we want to look at is we want to look at a neat way to use it. So what I'm going to do is I'm going to shrink this down a little bit and get it out of our way. And then we're going to take this example. So let's say, we're just going to pick two vectors. Now I'm picking these on purpose, but it'll be clear in a second why I chose these vectors. So I'm going to pick two perpendicular vectors, or in kind of the vector world, we usually say they're orthogonal. That's another word that just means the same thing. They're perpendicular vectors. And let's just call this one u and this one v. We like to use u and v for vectors. And so those are two perpendicular vectors. And then what we're going to do is try and find out what this vector is going to be. And the way we think of that is it's going to be a combination of our u and v vectors. And it turns out, I'll do it in red, if we take that v vector and just move it up here, remember we're allowed to move vectors around as long as we don't change their direction or their magnitude. So it's in red, but it's still just a v vector. And then, so I started, gonna try using my pointer here. So we started right here, and we added a v vector. And since we're trying to show this vector here, we want to end down here because the sum of our vectors, it always goes from start to finish. So let's try blue this time. So what I'm looking for is a vector from here to here, so that now I've started here and finished here. So I get that resultant vector that I was looking for. And you can see now I'm really just trying to form a right triangle here. So in order to get that, let's look at what that blue vector is. Well, that blue vector looks similar to our u vector here, right? The u vector goes here up, but instead we're going top down. So how do we switch vectors? How do we switch the direction? We just put a minus in front of it. So that is a minus u vector. So now we can go and label this not u, it's v minus u, right? Because first we did our v and then we subtracted a u vector. So v minus u. So now that we have a right triangle, let's put to work our Pythagorean theorem, and we're going to see what we can come up with here. Now, I know I'm kind of leading us through this, but it'll make sense in a bit. So to do Pythagorean theorem, remember, we'll do a little Pythag. We know that we have a squared plus b squared is c squared, where a and b are the legs of our triangle and c is our hypotenuse. So let's kind of do that with our vectors. Now remember, we need to use our magnitude of our vector, right? So the way we denote magnitude of a vector is with these little absolute value lines here. So there's the magnitude of v the magnitude of u, and I'm just going to put magnitude around that so I don't have to scrunch it in there. So now we're going to translate that over to Pythagorean theorem. So our a, let's call it the v. So the magnitude of v squared plus the magnitude of u squared is the magnitude of v minus u squared. So at this point, what we're going to do is we are going to substitute in what the actual magnitude of these vectors are. And just for the sake of simplicity, let's use the coordinates that we did up here in this problem. So we'll let u be a comma b, that'll be our vector, and the vector v will be c comma d. So we'll just reuse those. And so then our magnitude of v is going to be the square root of c squared plus d squared, and we need to square that. And all that comes from is essentially another mini Pythag with just that vector, right? So we just need to square the components and add them together and take the square root to find the magnitude of a vector. And for the u, it's going to be the square root of a squared plus b squared. We're going to square that. And this is going to be a little too big, so what I'm going to do is just shrink this a little. So that is the left side. Now the right side, we have to do the magnitude of v minus u. Well, to do v minus u, we just subtract the u components from the v components. So what that's going to look like is the square root of, now the magnitude of the x is going to be the v minus the u. So let's say it's going to be c minus a squared. And now for the y part, we're going to do d minus b squared. And because of our Pythag, we have to square that whole thing. Now let's see if we can do some simplification here. Well, since we've got this whole thing in a square root and we're going to square it all, same here, we've got the square root all squared, square root all squared, those are just going to cancel out. So we can rewrite this a little simpler now as c squared plus d squared plus a squared plus b squared equals c minus a squared plus d minus b squared. And now the left side looks pretty simplified, but what I'm going to do is FOIL out the right side here. So we're going to have c squared plus d squared plus a squared plus b squared equals, now to FOIL that out, I'm going to get c squared minus 2ac plus a squared plus, now we're into the second one, d squared minus 2bd plus b squared. Now, hopefully, some interesting things are going to happen here. I could subtract both sides by c squared. I can subtract both sides by d squared. I can subtract both sides by a squared. I can subtract both sides by b squared. And we're almost at the cool aha moment here. So there's 0 left on the left side. And then what's left on the right side? Well, we've got minus 2ac minus 2bd. And just to simplify this a little more, what I'll do it in 2 steps here. If I factor out a negative 2 from that side, I get AC plus BD. And then I'll divide both sides by negative 2. Since 0 divided by negative 2 is still 0, we get 0 equals AC plus BD. And if we look back, I know it's shrunk down a little bit, but what is our dot product? Well, u dot v. So any two vectors, and remember, we used the same coordinates that we did in our setup for the dot product, right? Just a comma b, any old real number. So it is AC plus BD. Well, look down here. We've got 0 equals AC plus BD. So what does that mean? Well, we can rewrite it as 0 equals u dot v. So now let's try and make some sense of this. We've got 0 equals u dot v. So the dot product is equal to 0. But in which case is it equal to 0? When the vectors are orthogonal to each other. So this is a really neat identity that we get. It's a theorem with the dot product, and we just proved it using two orthogonal vectors. So the dot product of perpendicular or orthogonal vectors is always going to be equal to 0. So now what I want to do is do a little continuation. And now what we're going to do is look at these two vectors. And let's just call them v and u again, just for simplicity's sake. And these vectors are clearly not orthogonal. They're not meant to be. And we can call that angle, theta is usually a good name for an angle. And what we're going to do now is look at what happens with the dot product of these two. Now, we're still going to get, just like in that last one, we're going to need to use this vector. And that vector is still going to be the vector v minus the vector u. But we can't use Pythag this time. Unfortunately, without a right triangle, we cannot use Pythagorean theorem. So what we're going to use instead is something called the law of cosines. So the law of cosines says, let's put it in a different triangle just to make it easier. So there's a triangle, not a right triangle. We'll call that theta. Let's call this A. Let's call this B. Let's call this C. And what the law of cosines is going to say is that C squared is going to be equal to A squared plus B squared. Now, that looks a little fishy. We're not done yet, but that right there looks like Pythagorean theorem. But what it does, now remember, because Pythagorean theorem is only for right triangles, we're going to have to take away a little something because it's going to end up having an extra term here. So we're going to have 2 times A times B, so there's those other two sides again, times cosine of theta. And that's why it's called the law of cosines, because we're going to end up using the cosine function here. So this looks similar to Pythagorean theorem, but it allows you to find the, quote, hypotenuse, the third side of a triangle, without having a right angle in between. So all we need to know is, we need to know this side, and the angle in between them, and we can find that third side there. And there's many different applications of this, and the way we're going to use it is we're going to use it to bridge the gap that we were able to make with the Pythagorean theorem in our last example. So what we're going to do is we're going to try and write out a similar expression to what we did last time. So we've got our comparison over here. We've got our template for our law of cosines. And what we're going to do is put in our vectors. Now remember, we're still going to have magnitude v, magnitude u, and I'll just put them there, magnitude v minus u. And we're going to need to put those in for C, A, and B. All right, so let's say that C is our v minus u magnitude. So I'll rewrite it. So v minus u, and we're going to have to square that, right? Equals, and let's do our v squared plus our u squared. And then we need to take away 2 times the magnitude of u, magnitude of v, times cosine, and we'll just call it theta, so there's theta. All right, now let's assume that we're gonna need components for these, so let's just say u is a comma b like we did last time, and v is gonna just be c comma d, just so we have placeholders for those. So let's go through and look at, now we have all terms that we know how to find. We haven't dealt with the cosine theta before, but we'll deal with that when we come to it. So let's go through and look at our magnitude of v minus u. So if you remember from before, I'm going to just skip a couple steps. The magnitude of v minus u squared ends up coming out to be c squared minus 2ac plus a squared plus d squared minus 2bd plus b squared. All right, then we've got to do the magnitude of v and the magnitude of u. So that's just going to be a squared plus b squared plus c squared plus d squared. And then I'm going to leave these last magnitudes. And again, I'm just going to kind of lead us through this. It'll make sense in a second. So I'm going to leave it as 2 magnitude of u, magnitude of v, cos theta. And that'll make more sense in a second. So now we can do our fun canceling. C squared, a squared, d squared, d squared, b squared, b squared. And what we're going to get is minus 2ac minus 2bd equals minus 2 magnitude u, magnitude v, cosine theta. We can factor out a negative 2 and divide. Actually, let's just divide everything by negative 2 right off the bat. So then we get AC plus BD equals magnitude U, magnitude V, cosine theta. All right. So now let's look back. You can look back earlier in the video where we saw the dot product. Notice that this right here is our dot product. So I'm going to rewrite it as that was U dot V. And that's equal to the magnitude of U, magnitude of V, cosine theta. So why did I leave those magnitude UVs in there and not simplify them out? Because this ends up being a really neat way to find the angle between two vectors. So we'll come over here and let's solve for the cosine of theta. So the cosine of theta is just the dot product of the vectors divided by the magnitude of those vectors. So once you go through that whole step, now remember the process of this was very similar to what we did previously. We just had the extra little hiccup of not having a right triangle. So once we go through all these steps and once we know what the law of cosines gives us, we can get to a nice expression that tells us that the dot product still helps us find out the angle in between the vectors. The orthogonal case is just a little cleaner because you end up getting 0, but it's still very useful to find the angle between two vectors.